All right. Hey, everybody. Welcome. Steve. Oh, hold on. David was in anticipation. I love it. Greetings, Tom and Steve from sunny Southwest Florida. Boy, you're a lucky dog. Jason, happy Friday. It is absolutely Friday, Fused Friday. That's right. Today is Fused Friday. I don't know if you catch Christy on her programs. I'm not sure what time she does hers. Hopefully, I'm not doing this at the same time she's doing hers. I have a limited time today, so I got 1 hour. So we're gonna pick up where we left off last week. Good, or I think it was last week. Steve, you're the man. Excellent. Thank you for. I'm glad you're enjoying the thing. So what I need, Steve, and everybody else, I need ideas after I do this next one, this next conductor. I want to go to small conductors, but give me an example. Give me something up. Give me something to work on. Give me some homework. So type down what the load is, what the conductor size, all that good stuff. If everybody has ideas, I'll try to find one and use that for our next one. But I want to go to small conductors next because overcurrent protection is going to be a little tricky in that application. And then I think I might also go into there was a question I had a long time ago that had multiple AC units on a roof and had a raceway where it was shared. I think I'll use that one as well. But we'll do various cases because I think moving forward, we've got the fundamentals in. Moving forward, we just need to flex our muscles with what we know and identify all of those areas where what we know doesn't quite match the field application, because there are some small conductors. There's small conductors is a good one. Multiple conductors in a raceway. And then I haven't even touched on 122, sizing the equipment grounding conductor, increasing the size and all that jazz, and adjustments for voltage drop. We're going to get there, though. All right. Eric Hammond in the house. Happy Friday. Joe, you are the man. Lunchtime with Tommy D. There's no better time. There's no better person that I can think of that you would want to spend lunch with. So, and we thank God we've got Don Kinnear. All right, and hopefully we'll get our friends from Minnesota to dial in as well. I think they're Minnesota or Wisconsin, maybe a little bit of both, and Utah. Anyway, all right. So we're talking conductor ampacity. If you recall, Cam A monitor. Right? All right, let me go back. Hold on. I got to get rid of that comment. Boom, because then it always comes up every time I go back to that scene. That's the wrong one. Monitor left. There it is. So I got the monitors mixed up. All right, that's fine. Oh, all right. So here's what we got. We went over conductor ampacity. We went through all the discussions of minimum size. We talked about the circuit ampacity. And we went through case one. So the case one, remember the case one was 4 current carrying conductors, 120 degrees, so a hot ambient. We're into the multiple conductors in a raceway factor that we have to apply. And then we know the conductors have a 90 degrees C insulation. And we were in one end of the conductor was terminating in 90, the other end in 75. What's Dawn saying? Dawn says a lot of people seem to have trouble with the small conductor rule. Yes, exactly, and that's my point, Dawn. So I would love to do a really good example. And remember, I think we want to flex the muscles to understand ampacity of the conductor and then ampacity of the circuit, but we don't want to overcomplicate it. So I think we start simple. And then we can go to a complicated application where maybe we have multiple branches or whatever. But I think that would be. I agree with you, and that's why I really want to. And I know, and I know I had trouble with the 240, Article 240, Section 240.4G requirements. So I think that was 240.4. Article 240 is overcurrent protection, and 240.4 is protection of conductors. Yep, and I do have to fix this. I've got to fix this. So here's what I'm going to do. I am going to do this, camera A, monitor right, and I got to fix this monitor. And I got to make this my tertiary. There it is. All right, because that way, and then I go camera A, monitor left, and I got to fix this one and make this my secondary. There we go. All right, so now we got that fixed. And Dawn, I'm with you. I am with you on that one. All right, so let's get back to camera A, monitor right. There it is. Okay, so remember last time we had 75 and 90. We had these conditions of use, and we ended up, and we're going to follow the same process. We're going to calculate, we're going to follow these 5 steps. We are going to calculate the current. Let's get these big. I'll move this over. Calculate the load current for 1.25 times the continuous load plus non-continuous. We're going to calculate the load current using only the conditions of use. We're going to select the larger of the two and pick our conductor that has an ampacity that can handle that larger number. Then we're going to evaluate the selected conductor to 110.14, considering the terminations. And then we're going to select our overcurrent protective device. So that's the process that we're going to use. We're going to stick to it. We're developing our PowerPoint. So remember, this situation ended up with a 1-aught copper conductor with a 110 amp circuit breaker feeding a load that had an 88 amps of continuous current. Okay, that's where we ended up. So now what we're going to do is we're going to take this not exact same layout, the same size conductor. We're going to take the same load, the same equipment, but we're going to specify that we have 3 current carrying conductors, not 4 or more. We are in a reasonable ambient of 86 degrees Fahrenheit, and we have the same 90 degrees C insulation. And we're going to take this and we're going to apply our process of calculating the load. We're going to follow 210. If you look in 210.19, because this is a branch circuit. Hey, Alan Bernstein in the house. Good to see you. And Jerry O'Connor from Chicago. Hopefully you're in Chicago. I'm not sure what part of the world you're in, Jerry, today. Jason. What does Jason have to say? Jason says, parking lot lighting circuit. Branch circuit, 20 amps. Multiple circuits in the same raceway. 3 circuits, single phase, 277, number 10, no ambient temperature adjustment. So here's my issue. Here's what I need, Jason. What I need is what the load is, what the voltage is, and the fact that we're going to use a 90 degree C, or actually just give me the conditions. We'll pick the conductor and then we'll determine the conductor size. You went straight to a number 10 and whatnot. So I want to start with the load amps and work our way back up. All right, so perfect. All right, Jason, Jerry, Alan Bernstein in the house. Gene Hernandez, welcome. Neetrac here, excellent. Okay, so we know in 210.19 that this governs the minimum ampacity and size for a branch circuit. It tells us that our branch circuit conductors have to have an ampacity that's not less than the larger of the two. First, I calculate to address continuous loads only. I don't do conditions of use. And the second, if I have continuous loads, in this case, it's all a continuous load. And then secondly, I have to address the conditions of use without the continuous load considerations. And Okay, Gene, it says don't forget derating. So, Gene, what we're doing is we're following the code, and remember, and we are following the requirements on how we determine the size of a conductor for the load. We're starting in 210. We know this is a branch circuit. I know I've got 88 amps. I'm going to do two calculations. One is not going to consider any adjustments to the ampacity. The other is going to be considering just the continuous loads, okay? Or the first calculation is just continuous loads with no conditions of use applied. The second one is we're going to apply the conditions of use and we're not going to apply the continuous load. The larger of those two, whatever it happens to be, is what I'm going to select. Okay? Perfect. Excellent. And then Alan says, unless equipment is rated less than 100 and then it is rated for 60. Ooh, ooh, ooh. And I've got equipment that's 88 amps continuous. Oh, boy. You know what? You know what I like about you, Alan? You know what I don't like about you, Alan? Is you always are right. You're right. That, Oh, no. No, here's the, oh, wait a second. Hold on, Alan. We're going to get to 110.14. So we're not going to worry about the equipment right now. So let's handle that muscle when we come to it. Okay. Oh. There we go. Perfect. That's what I needed, Jason. You're the man. Not derating. Yes, it's an adjustment factor. Very good point, David. It's a correction and or adjustment. You're absolutely right. All right. Yeah. Oh no, Alan. Nope. You're not. Not sorry. Okay. So here's what I'm going to do, Alan. We're going to. Here's the process. Remember, for everybody who's came to the last one, we will worry about the conductor only first, and then we're going to hit the equipment. And when we hit the equipment, we're going to go through 110.14. Calm down, Tom. I know I've got till 1 o'clock, so it's 12:12. All right, so these are the conditions. There's my load, 88 amps. I know my process. If I'm from Canada, it's my process. Here in the US, we will say it's our process. All right, so the first thing I do is, and I can delete this slide because I don't need it. Okay, the first thing I do, it says where a branch circuit supplies continuous loads or any combination of continuous and non-continuous, the minimum branch circuit conductor size shall have an ampacity not less than the non-continuous load plus 125%. So all of this is continuous, so 88 times 1.25 is 110 amps. So I've satisfied the first calculation. I don't do the conditions of use. I just do the 1.25. Excellent. Now, the second one says the minimum branch circuit conductor size shall have an ampacity not less than the maximum load to be served after the application of adjustment or correction factors in accordance with 310.15. Now, if we recall, I'm going to go back up. What slide am I on? Alan, what slide am I on? I'm on slide 77. I'm on slide 77. So we're going to come up to here, slide 77. I'm going to do a Control C, slide 77. I'm going to come down here to slide 77, and I'm going to go to 78, Control V. Now, remember the conditions of use. Oh, I grabbed the right slide too. In our case, the conditions of use, Control C, Control V. And I cannot see that at all. So I'm going to put this over because we know it's copper. I'm going to move these conditions of use over here on the right. Under the aluminum and copper clad aluminum because I'm dealing with copper conductors right now. All right, so I know I have 3 current carrying conductors. And what do I have here? Not more than 3 current carrying conductors. So I am meeting the conditions of use of table 310.16. I don't have to apply any adjustment correction factors for the number of conductors in a raceway. The second one is reference the ampacity correction factors where the ambient temperature is other than 86. And I am, look at that, I am 86 degrees Fahrenheit ambient. So I'm wunderbar. Okay, I'm perfect. So I'm at 86 degree Fahrenheit, and then my conductors have a 90 degree insulation. So I am within the conditions of use of table 310.16. Capiche? So what that means is for all of the conductors that are in 310.16, the ampacity that is shown under the 90 degree C column, I can carry that current every day of the week and twice on Sunday. I am golden with regard to the conductor. Now, we haven't talked about the terminations yet, but with regard to that conductor, I am within the constraints of that conductor with the ampacity values of the 90 degree C column for the conductor, for any one of those conductor sizes. We got that down. So we understand that the values of current in that table are based upon the conditions of use that are defined in the heading of the table and in the notes. And for any one of those columns, depending upon the insulation of the conductor, that current that is in that table, that conductor can handle that current all the time continuously. All right, so now what that means is if I go to 310.15, I don't have to do any percent values or multiplying factors because of the 3 current carrying conductors. So I don't have to apply an adjustment factor per that table. Okay, so I'm good with that. And then on the ambient, we said we were 86, but I know I have a range. So I've got 78, 79, 80, 81, 82, 83, 84, 85, 86. I got 9 degrees of latitude, of wiggle room, where I have a 1.0 multiplier. I'm at the top end of that. If my temperature was less, 78 to 86, then in fact, if it's less than 78, if it's in a nice air-conditioned room that's like 68 degrees all the time, then my ampacity actually goes up, right, by 4%. So I do a 1.04 multiplier. So as temperatures get cooler, I get better with my ampacity through that conductor. Again, forget about the equipment for now. Don't worry about the equipment yet. As temperatures go hotter, if I'm in an attic, I'm higher than 86 degrees Fahrenheit, now I'm applying adjustment factors, which, remember the last example, I was 120. So we were down around, for a 90 degree C, we were at a 0.82 multiplier. Now I'm at a unity multiplier. So what that means is I'm basically at 88 amps because I'm not applying any adjustment factors to that current, to the load current. So I've got my 2 values, right? And I got to change this. My conductor, based only on that, is 110 amps. And this was 88 amps. Okay. Larger of the two has to be selected. So I begin, let me go back to here. 88 times 1.25 was 110 amps. Here, 88 amps. I do the calculation, and now in this case, my continuous current was the larger of the two. If you recall, let's go back. Go back to where you once belonged. If we go back, it was the opposite. The conditions of use gave me a larger number. For the same example, same load, etc., my conditions of use generated a higher number because of the multiplying factors. So because of the ambient and because of the number of current carrying conductors in a raceway, I had to pick a different conductor. Now I'm just the opposite, where my continuous current times 1.25 gives me a higher number than the conditions of use. All right, so now I know I'm at 110 amps as the minimum. What did the code say in 210? 210 is simple and free. 210. 210. No, I'm in 240. Geez, oh man. 210.19. There it is. 210.19 tells us I have to have a conductor that has an ampacity not less than the larger of these two. In that case, my ampacity cannot be less than 110 amps. So that's the first gateway. So now if I come into the table and I go to the 90 C column, I'm really right there. Can I pet that dog? So I am right here at 115 amps based upon the 90 C column. For that conductor, based upon those conditions of use and a continuous load, I'm at a number 3. I'm at a 3 gauge copper conductor. I could use a bigger, I don't have my copper, I don't have my aluminum or copper clad aluminum, but we'll stick with copper for now. All right, so you can just do this and pick a different number, but you get the fundamental principle. Okay, so now I'm at 150 amps, so I know I'm at a 3 gauge conductor. So if I do this, Control C, Control V, 3 gauge, 3 AWG copper conductor with 90 C insulation. All right, let's get rid of that. I don't need that anymore. I don't need this anymore. Oh, and what we'll do is Control C, Control V, conductor. I don't need that. So I know I'm at a 3 gauge copper conductor. Let's do this. All right. Okay, so now I need to pick, what's my next step? I've done those. Oh, now I have to go to the evaluate for 110.14. Oh, okay. Man, I was having a brain fart. Okay, so now I have to pick, I have to do my analysis based on 110.14. So now I'm at a 3 gauge copper conductor. I know my equipment. Okay, so Alan, I love you, brother, from another mother. So if I go to 110.14, electrical connections, ba-dum-bum. All right, so what we're going to do now is, since Alan brought this up, let me just look at where I'm at. Since you've been gone, since you brought this up, I am going to do this. Equipment provisions. Control CV. So we know this is true. The lowest temperature rated equipment is the panel board. Now, why do we know that? I'm going to delete this. Why do we know that? Because Alan brought up a good point. Alan said, for equipment 100 amps or less, okay, and now if I'm going to do this, here's what I'm going to do. I'm going to tell you something over here. Okay, so this is 110.14c, and this is my equipment provisions. Now, what it says, the determination of provisions for equipment shall be based on A or B. Now, A is your 100 amps or less, okay? Now, if I say 100 amps or less, then I have equipment that's rated 90 C. Now, what this is saying is termination provisions of equipment of circuits rated 100 amps or less or marked up through 1 gauge, 14:1, shall be used only for one of the following. Conductors rated 60 C. Now, Alan, you mentioned this, right? So you said 60 C. You are, wait a second, all right, hold on. Generally, for equipment 100 amps or more is usually rated at 75 unless I special order. Oh, yes. And special orders don't upset us. All right. Alan, there is not much equipment below 100 amps that is rated for 60 degrees C. A few items. Okay, so Don, is where I was going, Alan. So here's it says the default is conductors rated 60 degrees C. Then it says conductors with a higher temperature ratings, provided the ampacity of the conductors is determined based upon 60 degrees C. That's telling you that I could use a 90 degrees C conductor in 60 degrees C rated equipment, but I have to use a 60 degrees C column. This third item, let me zoom in a little bit. This third item, conductors with higher temperature ratings, if the equipment is listed and identified for such conductors, that's the one, Alan, that I am falling back on. Because I have equipment that says it's rated for 90 degrees C. That means that the manufacturer has marked it that way. You raise a very valid, good point, and I think we touched on this in the last episode, maybe the previous, but I think it's worth coming back to. The reason that I am saying that the equipment, so whoa, shtakapukutuku. I'm going to say over here, the reason we are, the reason, the equipment rated less than 100 amps, in this case, is listed and marked for 90 degrees C terminations. Okay? This is permitted as per 110.14 Charlie, I think it's C. Yep, C1 A, oh boy, 3. Okay, conductors with a higher temperature rating of the equipment, if the equipment is listed and identified for use with such conductors. Actually, yeah. Does that fall under it, Dawn? Think about this. If my equipment is rated for 90 degrees C, it's rated for 90 degrees C. My conductor doesn't have a higher temperature rating than what the equipment is listed for, because the equipment is listed for 90 degree. So I'm having a little heartburn. Here's a few heartburns I have, Dawn. Here's a few heartburns I have with this language. I'm calling you out because here's my issue, Dawn. If you recall in 110.5, 110.5 tells us that a lot of people don't know this thing exists. 110.5 tells us that conductors used to carry current shall be of copper, aluminum, or copper-clad aluminum, unless otherwise provided in this code. So that basically opens the door to any size any type of insulation. But if it's not marked, it's going to be one of these three, unless I call it out. So if I say that it's a conductor, that means it's going to be either copper, aluminum, or copper-clad. But if I want, I don't know, a platinum conductor, I would have to call out a platinum conductor. And then it says, if the conductor material is not specified, the sizes given in this code shall apply to copper conductors. So here's my issue with that. Now, I know I have this sort of is a caveat. If other materials are used, the size shall be changed accordingly. So if I come down here to my 110.14, this says termination provisions of equipment for circuits rated 100 amps or less or marked 14 gauge through 1. That's copper only. I mean, would you agree? So does that mean that this doesn't apply if I have copper clad or if I have an aluminum conductor? It does say I have to adjust it appropriately. I'm just a little bothered with this one. So in any case, conductors with higher temperature ratings if the equipment is listed and identified for use with the conductors. That's what I'm going by. That's my story, and I'm sticking to it. Okay, so the lowest temperature rated equipment is the panel board, which is 75 degrees C. The ampacity of the conductor cannot be greater than the value of current for that conductor located in the 75 degrees C column. I'm hearing stuff. Equipment, equipment under 100 amps is assumed 60 degrees C unless marked otherwise. That's what I would say, Steve. All equipment 100 amps and over 75 unless marked 60 degree and some other older equipment. Yeah. So, but in this case, my equipment is marked 90 degrees C. And that would be per its listing. But I'm not sure if I agree with 110.14 Charlie 1A3, conductors with higher temperature ratings if the equipment is listed. It's the conductor is 90 degrees C, the equipment is 90 degrees C. So it should say conductors with temperature ratings that are equal to or greater than. That's what it should say. Conductors with a temperature rating equal to or higher than the equipment is listed if the equipment is listed and identified for use with those conductors. Or conductors with a temperature rating with any temperature rating if the equipment is listed and identified for the use with those conductors. Anyway, it's semantics, but I know we know what you know and you know. I special ordered. No, I didn't, Alan. An example is AC equipment per the listing standard for AC equipment. The terminations have been required to be suitable for 75 for a couple of decades. Yep. Eric Hammond says, from a design perspective, on a design bid build project, we don't typically know what the terminals will be rated in the equipment. We take the approach of sizing the conductors 100 amps or less at 60. Eric, good point, Eric. Jason, okay, now thank you, Jason, is stating, in your opinion, that if the conductor material is not identified, it is considered to be copper. That's what I would assume too. But then here's my issue, Jason. If I have a requirement in the code that says, I don't know, if I have a requirement that says, you must do X, Y, and Z for 14 through 1 gauge conductor, does that mean that only applies to a copper conductor? Then I don't have to follow those rules for aluminum or copper clad? What does it mean? That's my issue with 110.5. I think I'm having heartburn with it because as I'm reading down through here with 14, and somebody pointed out to me on one of these calculations, they said, well, that's for copper only. And I'm like, oh, whoa, wait a second. And then they pointed me back to 110.5, and I'm not liking 110.5. That's what I'm saying. Anyway, okay. Dawn, thanks for the info. I did not know that because usually deal with unit substations and medium voltage systems. Ellen. So, Ellen, you're always at 90 degree. Medium voltage, baby. Eric, I agree with your safe assumption. Yes, Eric, that is a very good safe assumption. You'll upsize your equipment. You know what I might do? I might do this based on 60. We're going to do this based on 60 if I got time. 110.5 says that the material is not designated to use copper. There is no conductor material mentioned in 110.14c, therefore it should be considered to be copper. So, Joe, Does that mean that the requirements of 110.14c don't apply to aluminum? That's my issue. If it only applies to copper, but I think the adjustment, so I would have to look at a 14 copper and say, what's the equivalent copper clad aluminum, right? So if I look at a 14 copper and man, what time is it? I got a hard stop at 1. If I look at copper, open a new tab. If I look at a 14 copper, let's go to 310. If I go to a 14 copper in 310.16, the equivalent copper clad aluminum is not in the list. You know where it is? It is in the 2026 www.nfpa.org/70 next panel 6 fix this issue. Oh boy, this is nice. Okay, so if I go to the 2026 code, the copper clad and a copper clad aluminum equivalent to a 14. I love it when this comes together. 310.1416 is bada bing. But where is it at? 310. I'm in 310. 310. 310.16. Ampacity. Oh, there it is. 14. It is a doom boom 10. Number 10. All right. So so that would mean that I would make the adjustment. Okay, this makes sense. You know what? I'm feeling better now. So if I had, like for copper clad aluminum, for an example, and I know that's a hot, busy topic, a 14, I never had an equivalent copper clad. I would have had to have gone up. I would have had to have gone up to a 12 to even get to a number. That would be the 15 amp copper clad aluminum. But what the 2026 code is going to let me do is say, look, I can do a number 10. So that ampacity value, or that termination allocation, because it says 14 gauge, the equivalent in copper clad aluminum is a 10. All right. I love it. I love it. All right. So almost no equipment. So you guys are going back and forth. So let me do this. I'm going to finish this up, guys. All right. So we'll get to your comments after. Okay. So now we know the ampacity of the conductor must not be greater than the value of current for that conductor located in the 75 C column. So we said we had a 3-gauge conductor, copper conductor. It can carry 115 amps. If I go to a 3-gauge conductor, I was at 115. Now I'm at 100. So I know I can do 100 amps. I can do 115 based on the 90 C. The copper ampacity is 115 amps based on the conditions of use for this application. Based on 110.14 Charlie 1A3, the 75 C equipment ampere rating is based on the 75 C column of the table. It is the weakest link. 310.16. I have to use the 75 C column, which is 100 amps. And I'm just going to highlight that. Boom. Whoa. Whoa, that gets a Joey. Whoa. Let's make this black. There it is. And then I say, based on this information, 88 amps is less than the ampacity of the conductor and the 75 C column of table 310.16. Hence, we have met the requirements of 110.14. Are we golden? Because when I use this, I have 88 amps of continuous current. This is just talking about the conductor with the terminations. The 1.25. Let me think about this. My termination cannot exceed 100 amps. I'm good. I'm good. I have 88 amps of load, so I am good with 100 amps. I don't have to do the 1.25 because that equipment can handle up to 100 amps continuously based upon the 75-degree C column. My conductor can handle 115 amps based upon table 310.16. So I'm golden. Okay, so now, all right, so now follow my logic. Now I got to pick, so I know I'm there. So I've done all that. Now I have to pick my overcurrent protective device. So I know my termination is good. My 88 amps isn't going to exceed the 75-degree C column for that number 3 or 3 gauge conductor. I can handle up to 100 on that 3 gauge. The 3 gauge conductor itself can handle up to 115. You're freaking golden. Now I got to pick my overcurrent protective device. Bam. All right. So I got a 3 gauge copper conductor. The 3 gauge ampacity is not that. Oh, yeah, it is. 115 amps times uno times 1. Let me move this over. Whoa, do you stun a maganyo? How do I move that over? I can't. It's not tabbed, is it? No. Anyway, my conductor ampacity is equal to 115 times 1, which is 115 amps because it's 3 gauge. My circuit ampacity is 100 amps based upon the 110.14, so I can't exceed 100 amps on this circuit. I'm at 88. Good to go. I select an overcurrent to protect the device to provide 100 amps of protection because I got to, because of that minimum, that maximum requirement. Remember, my circuit ampacity, which is limited based upon the 75-degree C equipment, I can't go greater than 100 amps on that number 3 conductor. So what do? I pick a 100 amp breaker. Boom. So now I know I got a 100 amp breaker. But remember, based upon for the ampacity of 100 amps and OCPD of 100 amps is permitted, 210.28 requires that the rating of the OCPD, not be less than the non-continuous plus the continuous. So my OCPD cannot be 100 amps. It has to be at least 110 amps. So that means I can't do a 100 amp breaker. Ain't gonna happen, not gonna work, 1,000 points of light. Okay? So, and the reason I can't is because I have 88 amps of continuous current. I need to take 1.25 times that continuous current, then select my overcurrent device. My overcurrent device has to be greater than or equal to that number. In this case, I have a 100 amp breaker. So I can't do it. So, what do I do? I go to the next standard size, and I go to Article 240 for the standard size breakers. Article 240. 240.6. I had 100 amp. I could go to 110. I need to increase the conductor size. That's what I need to do. I need to increase the conductor size. So, boom, boom. Let me grab this slide. Let me come back down here. Let me put this in here. If I can't use this one, I could go to a number 2. Right? I can go to a number 2. I can increase the conductor size. Let me do this. Increase conductor size from 3 gauge to 2 gauge. This gets the equipment up to 115 amps of capacity, of capability. and the conductor at 130 amps, period. 88 amps of continuous load yields an OCPD that must be equal to or greater than 88 times 1.25 equals 110 amps. So I could put a 110 amp breaker on here. And 110 amps is a good one. Boom. A 110 amp circuit breaker, or large, or because I got 115, I could 110 the circuit breaker can be anywhere from 110 amps to 125 amps. And why is that? 110 amps is less than 115. But that's the minimum I need, 88 times 1.25. It's less than the ampacity of the circuit, much less than the ampacity of the conductor, which is up at 130 amps. 240, Article 240 lets me go to the next higher size. If I'm at 105, if my circuit ampacity is 115 amps, the next higher size circuit breaker is 125. So I can put anywhere from 110 amp to 125 amp. 110 amp is the minimum because it's 1.25 times 88. 125 is the maximum because of Article 240 lets me go to the next higher size. And that would be 240, next higher size is 240 dot, oh man, it's up here. No, I'm sorry, 210.28. No, next higher size is 240.4. 240.4b. Okay, so 240.4b. Okay, I'll put a thing. 110 amps because, what the heck? Control Z. 110 amps because that is equal to or greater than 1.25 times 88. 125 amp because of 240.4. 240.4 B. Is that 240.4b? Yep, 240.4b because I can go to the next higher. So that gives me my range. So if I come down to the next slide, I say I'm going to put 110. Why would I spend money on a 125 amp breaker when I can just do a 110 amp breaker? This circuit breaker can be as small as a 110 amp breaker that would not be less than 125%. Yes. All right, perfect. And I said it can be as great as 125 amp. So I put a 110 amp breaker. I got a 2-gauge copper conductor. What time is it? Oh boy, I got 10 minutes. 2-gauge copper conductor. Boom, boom, boom. 115 amps at 75 degrees C. Bam. 1.25 times 88 is 110. Boom. A 110 or 125 amp circuit breaker is permitted because the rating of the OCPD is greater than 1.25. Blah, 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 blah. Perfect. Boom. I don't know why I have this here. Boom, boom. Oh, you know what I'm going to do? Here's what I'm going to do. I'm going to take this. Control C. I'm going to put this over here. I'm going to do a Control V. And I'm going to basically say what we did. We increased, using my mouse, we increased the conductor size from 3 gauge to 2 gauge. That's the first thing we did. The increase places the equipment current rating for that size conductor at, whoopsa-daisy, at 115 amps. The conductor ampacity based on 310.16 is 130 amps. We must protect the circuit at the circuit ampacity of 115 amps. The minimum size OCPD is equal to 88 amps times 1.25 equals 110 amps. The maximum size OCPD based on 240.4B is the next larger size to protect. Oh, wait a second. No. No. Dawn, I need you, brother. Everything I've heard of with the 1.25, the 240.4 says conductors. The next higher standard overcurrent device above the ampacity of the conductor being protected shall be permitted to be used provided all the following conditions are met. The conductors being protected are not part of a branch circuit supplying more than one receptacle. The ampacity of the conductors does not correspond with a standard ampere rating. The next higher standard rating select does not exceed 800 amps. If the overcurrent protected device is adjusted. So this is not a conductor value. I can't go to the next higher for the equipment rating. The equipment, the ampacity of the conductor. Ooh, this opens up a bag of worms here, Dawn. It says the next higher standard overcurrent device rating above the ampacity of the conductors. The ampacity of the conductors, in this case, the ampacity of the conductor is 130 amps. The ampacity of the circuit is only 115. I can't exceed, I don't have any permission to exceed the ampacity of the circuit. So I can't go. This is wrong. The circuit breaker can be as small as a 110 amp circuit breaker. The circuit breaker must be no greater than a 110 amp circuit breaker. No, that was right. Control Z. Yeah, can be as small as a 110 amp circuit breaker, as that would not be less than 125% of the continuous load. That's true. That is true. The circuit breaker can't be greater than 110 amps. The circuit breaker cannot be greater than 110 amps. No, it can't. No, what am I talking? No, that's right. That is right. Jeez. Can be as small as 110 amp breaker. I can't go less than 110 amps because that would be less than 125%. So that's an accurate statement. And that's an accurate statement. So that's my smallest value. The circuit ampacity is what? 115 amps. The breaker cannot be greater than 115. We must protect the circuit at the circuit ampacity of 115 amps, period. The minimum OCPD size is 110 amps. The maximum size OCPD is 115 amps. The maximum size OCPD is 115 amps because that is the circuit ampacity based on the equipment. I can't exceed 115 amps through that with that size conductor for the equipment. It has nothing to do with the ampacity of the conductor itself. It's the equipment that is the limiting factor. All right. Okay, I got to go through this. Hold on. All right, so let me do this let me finish this. I got it's 10:56, so bear with me here 1 second. So that means that I have a 110 amp breaker with a 2-gauge conductor, 110 amp breaker, 2-gauge copper conductor, 3 current carrying conductors, 78 to 86 degrees ambient. Conductor has a 90 degree C insulation, 88 amps, 90 degree C. That's it. So I'm at a 2-gauge copper. My result for the previous was a 1/0, I believe. Yeah, was a 1/0. So this, because I don't have the same conditions of use, it's just based on the continuous load. I'm at a 2-gauge. So the conditions made a big difference for the sizing of this conductor. All right, so that's now I'm going to take let's go to the notes. That's a good point, Tom. Looks like the wire size should be removed or adjusted. Hold on, I got to see where I was at. See that? 110.5, materials not designated you as copper. There is no copper. Okay, I remember that discussion. Alan, that's a different world. 105 degrees C, as I recall. That is correct, Dawn. Steve says almost no equipment is rated 90 degrees C. Okay, we were talking about the 90 degrees C. I'm with you. I think you would have to reference 310 if it's other than copper. Yes, and that's what I did, Jason. Joe Ballard says that's a good point, Tom. Looks like the wire size should be removed or adjusted. You know what? I would tend to agree that we got to really be careful on how we use that term. When we say 14, if we just said 14 gauge, like for example, in here, in 210, it says for a branch circuit, the minimum wire size, the branch circuit, minimum wire size, branch circuit ratings, so 210.18, 19, branch circuits, 19, 20, minimum branch circuit, minimum. Where's the minimum? Minimum, hold on, Control F. Minimum. The minimum number. Minimum. Minimum requirements. The minimum number. (14 AWG). All right, the maximum length. All of these, these are all copper only. Other loads. There it is. Branch circuit conductors that supply other loads than those specified in 210.3 and other than cooking appliances. Okay, so this is in 210.19, 210.19D. 210.19D, it says branch circuits, conductors that supply loads other than those in 210.3 and other than cooking appliances in 210.19C shall have an ampacity sufficient for the load served and shall not be smaller than 14 gauge. So now I have a 14 gauge copper, which is a 10 gauge copper clad aluminum. So I can't have less than, at least based upon the 2026, I can't be smaller than, for branch circuits, other loads, smaller than a 14 gauge copper clad aluminum, or 10 gauge copper clad aluminum, 14 gauge copper. All right, so that makes sense. Joe, I think that needs a little bit of attention. If I'm thinking right. Where was I? Where was I? Geez, oh man, where was I? Where's your note? Steve, this is Joe Bellantoni. Joe. Jason Doty, Steve Spiker, Don Gannier, Jason Doty, Alan Bernstein. There it is. That's a good point, Tom. I'm looking for that's a good point, Tom. There it is. Okay, next one. I want to thank everyone for their comments. Excellent, Alan. Anybody who learns, I'm learning too. Excellent. Thank you. Jason, because 110 is general, the only thing I would see is using 310 for other than copper. Yeah, you're right. Yep. Do we not require the circuit ampacity to be 88? The circuit ampacity, no. No, Alan. So the only reason we do the 1.25 is for the overcurrent protective device, right? Because the code says the overcurrent protective device has to be greater than 1.25. I don't have anything in the code that says that the termination has to be greater than 125% of the continuous. I do the two numbers for the ampacity, the conductor, pick the larger of the two, and I move on. So 240.6. 240.6. 240.6. Yes, 240.6 is your standard ampere ratings, and that's, again, overcurrent protection. So, all right, Alan, that's where my head's at, Alan. Okay, I get it. 240.6, table. Yes, that's the standard ampere ratings. Do I want to be evil? Oh, and ask if you are using a standard multi-case or I'm using a standard 80% rated. If I was at 100% rated equipment, because remember, Alan, it's not just the breaker that matters. The equipment also matters. I might need a panel board with a high density copper, all that jazz. All right, yes, I'm being evil. I know. All right, guys, I'm missing another call. I apologize. I've got to run. Thanks, everybody, for joining in. I've got another call to get on. Thanks for joining in. Thanks for what you do for the electrical industry, and thanks for what you do for electrical safety. Take care, stay safe, and please stay healthy.